Welcome to Unit 6, Integration. We did some of this at the start of the year when we did our calculus overview. This is the other big idea in calculus after derivatives. Integrating is finding the area under a curve bounded by the x-axis, usually from one x value to the other. So we are going to first use our calculator to find the exact area bounded by the curve f of x equals x squared. So really this is the y-axis here, the x-axis. We're only looking at it from x is 0 to where x is 1. And so we don't see the entire parabola, we just see it here. And I really blew this up so we could go by basically quartering from 0 to 1. And you'll see why. So get your calculator. We're going to go through finding the actual area first. Remember what we're doing to find the exact area. What does that mean? To find the exact area, it means we're doing this. We're finding the integral from 0 to 1 of our function. So I'm going to write the actual function in here, x squared dx. And I'm totally ignoring Riemann sums for right now. We're just taking a look at what this means. So it means finding the area from this curve down to the x-axis. So that's our vertical bounds. So this is the curve. Here's the x-axis from x is 0 to where x is 1. So it's all this area under here. And our calculator can do that for us. So go ahead and put your function into y equals, so you want to enter an x squared. And then we really only care about a little bit of it. So let's go to our window and let's set our x min to -1 and our x max to 2. Remember, that's always like a good thing to do, go like one less and one more than you need. Your x scale can just be 1. If you want to make it 0.25, you can to look exactly like what we're doing. It doesn't really matter. Our y min, we don't need, obviously there's no negative value, so your y min can be -1. We're only going up to 1 here, so we can make our y max 2. Okay, let's graph it. And then we can see basically what we have on the screen here. So go ahead and let's find the exact area underneath this curve. What we're going to do is we're going to hit second trace to calculate. And then down to number 7, you can see that there's the symbol here, the integral symbol. Go down to 7. It asks for your lower limit, 0. That's this number right here. Click 0, hit enter. Your upper limit is 1. 1, hit enter. And it fills in the area under here, under the curve. You should get a third. And it'll tell you that it's exactly 1/3. Now, we are able to estimate this value using what's called Riemann sums. Riemann sums are a way to estimate this value if we weren't able to find it exactly. For instance, before I teach you the exact way to do what we just did on our calculator, like we'll be able to do that by hand eventually, but Riemann sums are a way of estimating the area under a curve using rectangles. So we can have 3 different types of Riemann sums: left, right, and midpoint. We're going to go over those 3 in today's lesson. It's really not a difficult idea. The main idea that you have to remember is that the area of a rectangle is base times height. That's it. If you can remember that, then you can find a Riemann sum. So let's approximate. Let's first do a right Riemann sum approximation. All right, I decided to do 4 equal subintervals. That's already how I had this example set up. Sometimes the subintervals will be equal, sometimes they won't be. We'll explore scenarios where they can't be equal. Basically, we want to create 4 different rectangles starting from the right between 0 and 1. Therefore, each rectangle's base is going to be 0.25. That's the only way to split the distance between 0 and 1 into 4 equal subintervals. So I'm just going to draw these rectangles. Once you do this a couple times, you won't necessarily need to draw it, but I just want to show you what we're doing. So I'm going to do this in red. All right, so my first rectangle is going to go, again, these lines aren't perfectly straight, but they are designed to be, or they're supposed to be, rather. That's my first rectangle. I'm starting from the right, and so my height is going to be determined out of this base length here. My height's going to be determined by the rightmost x value. My height is 1. How do I know that height? Well, I know that height because the height is my y value on this curve. My y value here, when I plug in x is 1 into my function, my height is 1. So this first rectangle here, I'll call it r sub 1. The area of that rectangle is base length. What's our base length? It's 0.25. Times my height. My height is 1. So the area of that first rectangle is 0.25. I'm just using decimals in this problem just for ease, but you could totally use fractions if you want. It doesn't really matter. Okay, our next one, it's a little bit harder to see the height, but our next one, we'll do in a different color. We'll do green. Our next rectangle is going to have the same base length, and its height will be determined by the height that 0.75 yields. So this is our r sub 2 in green. Again, our base length, they're all the same because they're equal subintervals. Our base length is 0.25. Now what's our height? Well, our height is whatever we get when we plug in 0.75, this x value, into our function. It's the y value. So you can use your calculator for that, which I will. And if you want to go into your table and just plug in values into your table, you can. If you just want to use your calculating screen to do 0.75 squared, that's fine too, 0.5625. Then we'll multiply those together and get 0.140625. Cool. All right, let's do our third rectangle. I'll go back to, we'll do black. This one will be here. This is r sub 3. And I'm not using r for rectangle, I'm using r for right, Riemann Sum, just so you know. All right, go ahead and figure out what the area of that rectangle is. Pause the video. The answer will pop up on the screen in a second. Okay, our third right Riemann sum, our rectangle will give us an area of 0.0625. And our last one is very small. It's our fourth one. Again, our base is 0.25. And our height is determined by squaring that value. Again, because our height is the y value here on our function, determined by plugging in 0.25. So we can square 0.25. And we get 0.0625 for the height. When we multiply those together, we get 0.015625. Okay, how do we find our right Riemann sum? As the name suggests, we find their sum. We add all four of them together. So in your calculator, go ahead and add the areas of those four rectangles together, and you will get your right Riemann sum. We found the right Riemann sum to be the following decimal. Once you have that in your calculator, you can always hit the math frac button and you'll get 15/32. Sometimes we do things in fractions. We could have totally done this one in fractions. I just picked decimals, I thought it was easier to explain that way. I'm going to clear the screen now, but leave the rectangles up. I'm going to show you how you can do this in maybe a simpler way, but I just wanted us to draw and see that that's all we're doing is we're finding areas of rectangles. The only difficult part really is getting the heights. Again, this is a right Riemann sum. We're going to do left Riemann sums here in a minute, and they're going to be shorter rectangles. But these are taller rectangles because our x value that's to the right of each rectangle, so in the red rectangle, like 1 is to the right of 0.75, that yields a taller y value. So that's why our right Riemann sum will be a larger number than our left will be. All right, is there an easier way to go about this? Sure, there definitely is. We know that the base of each one of these is 0.25. So essentially we're taking 0.25 and we're multiplying 0.25 by 4 different heights. So I can basically take 0.25 out front and then just have the 4 heights here on the inside. Now what are those heights? Those heights are determined by the function basically. So our heights are each of these x values squared. So we can write it just like this. This one's 1 squared. This next height is 0.75 squared. The next height is 0.5 squared. And the last height is 0.25 squared. Again, that's because our function is the x value squared, and our heights are just the function values, the y values at those 4 locations. If you plug it like this into your calculator, it's a little bit more straightforward than finding 4 separate values and having to add it together. You get the same value. We call this r sub 4 technically because it's the 4 added together. All right, let's take a look at our function from 0 to 1. Our function f of x is clearly increasing here, right? It has positive slope. And we can see that if we found the first derivative, it would yield positive values. Anyway, since our function is increasing, you can clearly see that the rectangles that we drew from the right are much larger than the actual area underneath the curve. We found, remember, the actual area to be 0.3 repeating, and this is clearly an overestimate of that. You can visually see how these rectangles overestimate the actual area underneath the curve. A lot of times on the AP exam, it'll ask whether or not one of our Riemann sums is an under or overestimate. This one's an overestimate, and the reason being is because f of x, our function, is increasing. Therefore, the height from the right is larger than the height from the left. So f of x is increasing on 0 to 1. Okay, I'm going to go through the left Riemann sum a little more quickly just because we already have the idea. So this one won't take us as long. We're just going to go from the left. Now going from the left, you're going to see an issue right off the bat. Since our leftmost x value is actually 0, which we didn't include before, this first rectangle has a height of 0, like it doesn't exist, right? So we're only going to have 3 rectangles here. Our first one has a base length of 0.25, but a height of 0, because when we plug 0 in, we get an output of 0. So we don't even have that rectangle at all. So let's do our next one. Our next one, that was a pretty bad rectangle, but you get the idea. There it is. This rectangle right here is going to have a base length, once again, of 0.25, right? That's the distance between the x values, but a height that is shorter because this height is now on the left side of the rectangle. So let's do our left Riemann sum in the shortened way. So all of them are going to have base lengths of 0.25. And then our first height, like we said, was 0. So when we plug 0 into our function, it's 0 squared. Plus our second height is determined by this x value. So when we plug it in, we'll get 0.25 squared. Go ahead and think about what your next two heights would be. Pause the video and the answer will be on the screen in just a minute. Okay, our left Riemann sum with 4 equal subintervals ends up giving us a much lower value than our right Riemann sum and a lower value than the actual area under the curve, which again was 0.3 repeating. So L sub 4, which means the left Riemann sum with 4 equal rectangles, rectangles of equal, base length here, subintervals, is 0.21875. We can clearly see that because our function is increasing, we've established that those leftmost heights are never going to quite reach the height that we'll eventually get to for that rectangle. So these rectangles are a pretty severe underestimate of the actual area. So when we're asked about the left sum, we can say that this one is an underestimate of the actual area because, once again, our function f of x is increasing. And I realized when I wrote it last time, whenever we're saying increasing or decreasing, I technically should have open parentheses there. Or you can also say from, like that, from 0 to 1 on the x-axis. Okay, the last type of Riemann sum that we're going to study is a midpoint Riemann sum. This one's probably the most difficult just only because it requires the most extra work. I wouldn't say the work is technically difficult, it's easy to make an error, so just be careful. What I've done is I have found the midpoints, and I started here because this gets very squished and it's so small. So that's the only reason I started from the right. It doesn't matter where you start. Again, remember we're going from x is 0 to x is 1, 4 equal subintervals. That's why each subinterval is 0.25. Okay, so I found the midpoint between 0.75 and 1. If you need a refresher on finding midpoint, it's the average. So you add 0.75 and 1, then divide by 2. Please be careful with PEMDAS and order of operations in your calculator. First add them together, hit enter, then divide by 2. Or when you add them together, please, for the love of everything math, make sure that you put it in parentheses, then divide by 2. If you don't put the parentheses, it does this first, and that is not good. Okay, so now that we've established the midpoint x value, which these all make logical sense that they're directly in between, all we do is we find the height that way. So we find the y value that 0.875 gives us, which is whatever 0.875 squared is. And it looks like it's 0.75. Cool. So then we're just going to do that and find those 4 rectangles. So I'm just going to go through again, finding the areas of those 4 rectangles. We'll add them together and that'll give us our midpoint Riemann sum. Okay, so I have the first base and height of this rectangle. So in our calculator, we can do 0.25 times 0.875 squared. Again, that's the height. And it's a super long decimal, so I'm just not going to write these all out. And instead, I'm going to just show you kind of what we've been doing by writing it all one time. This saves you a ton of time. So our next one, I'll just get a different color and do it that way. The 0.6, and I'm only drawing this dashed line to show you that that's the height. You don't need to draw the dashed line. But as you can already see, this is kind of like, this is definitely a better estimate than just the left or the right Riemann sums, just because it's like a little bit over the curve, you know, a little bit under the curve. It's not overestimating or underestimating as severely as the left and right were on their own. So, okay, let's look at this one. Again, the base length is 0.25 and our height is what we get when we plug 0.625 into our function, which is 0.625 squared. Our next one will be the height provided by 0.375. That's our other midpoint. So that one is 0.25 times 0.375 squared. And our last one is tiny. And it's the height, or sorry, the base of 0.25 and the height provided by our x value of 0.125, so 0.125 squared. I'm going to enter this into my calculator, see what I get. Actually, before we do that, I want to show you something. We could just really write this, right? They all are being multiplied by 0.25, so the 0.25 can come out front. And then we can literally, this is what I did for the left Riemann sum. We just add all these four values together. And this is the easiest way to enter it into your calculator. That way you're not having like a million decimals all over the place. And you can just get one nice answer at the end. If I don't run out of room. Okay, so we'll put this into our calculator and see what we end up getting. Okay, we end up getting 0.328125 for our midpoint. And that'll be M sub 4, a midpoint Riemann sum with 4 equal subintervals. That's way closer to the actual value of 0.33. We really wouldn't have a way of knowing if the midpoint Riemann sum was an over or underestimate. Like clearly we know it's an underestimate because it's less than 0.33 repeating. But my point is that like we wouldn't just know that unless we knew the actual value first. These are a lot harder to tell. And it's barely an underestimate. All right, so what the heck is the point of doing this if we can find the exact area under the curve? That's a great question. It's mainly so when we don't have a function and we only have values from a table, we can't find the actual value. What we need to do is estimate it using either Riemann sums or trapezoidal sums. So essentially, this is not going to be something you're probably going to do on the AP test exactly, but you definitely will do it using a table. For teaching purposes, I teach the function version of it first because I think it provides a much better visual than the table one. We will work on tables tomorrow. What I'm going to do next is provide for you an example problem that looks similar to this, basically a graph, and have you find the right, the left, and the midpoint Riemann sums. You can use your calculator, that's great. And then I'll provide the solutions and then your homework. Okay, so here is your practice problem that you should definitely also be putting in your notes. I want you to approximate the definite integral of 1 over x dx from 1 to 3. That means you want to find the area beginning with x is 1 and ending when x is 3. I want you to do this in 3 different ways: a right, a left, and a midpoint Riemann sum, all with 4 equal subintervals. If you feel like you have it at this point, pause the video, do your thing, and then fast forward a little bit to check. I'll have the answers up here in just a minute. If you feel like you need some extra hints, I will give you just a couple, and then you can pause and do your thing. Okay, here's your first hint. If you need 4 equal subintervals, think about what the length, like your total x length is. So your total x like length is 3 minus 1, right? It's 2. So you want to know how long should I make each delta x, right? Change in x. How long should each base of my rectangle be? Well, it basically should be the entire length, which is 2, which you get by doing 3 minus 1, and dividing it by how many rectangles you need. You want 4 because that's what you're told, right? So basically you have a length of 2 and you want to split it into 4 equal parts. Clearly each base should be a half unit long. So this is one length, one base length, this is your next, this is your third one, and that's your fourth one. Remember, right, left, and midpoint simply tell you how to find the heights of each rectangle. So for your first right Riemann sum, this is the base of your rectangle, the height is provided by your right point. So it's by plugging in 1.5 into this function here, 1 over x. Your function's 1 over x. How can you find those values? Well, an easy way if you're using your calculator is to just make an XY chart. Oops. Plug in all the values, plug in all the x values that you'll eventually be using. Then figure out what your y values are using your function. Okay, those are your hints. Go ahead and pause the video, do A, B, and C, and then click back on to check your answers. Okay, here are the solutions. If you did not get these, look back through your work, or you can ask me on Zoom, but I really would make sure, go back through, that's the best way of learning. Remember, practice makes you great. The struggle is good when you learn. It really stretches your brain. You guys got this. This isn't too bad. Tomorrow we will take a look at Riemann sums using tables, then we'll get into the trapezoidal rule. Okay guys, last part. Your homework for today is this one problem. So please do this on a separate sheet. It is super helpful to sketch the function. A lot of us are very visual. It really does help, I promise. Create an XY chart. We didn't really do that too much, but if that helps you to organize your thoughts, that's awesome. Use your calculator when in doubt. You are working from home. Please use it. Also, we're only going from x is 1 to x equals 2 using 4 rectangles again. So remember, this is only a distance of 1 unit, right, from 1 to 2. And you want to split it up into 4 equal parts. So just use common sense, right? Figure out how long each base should be of your rectangle. Good luck. Ask me any questions on Zoom, and please upload this to the Dropbox on Blackboard. Have fun.